Jag ska försöka igen då, det får väl bli med Ron.
Okej, tack.
Ja, tack Stockholm. Okay, so I will... Do you see me?
Vi ser Erik från vänster, helbild.
Okay. Okay, great. Hi, everybody. Okay, so my name is Erik Ytterberg. I'm a senior researcher here at HullMASTER. So, as Lena mentioned, and also Åsa mentioned, that we've been working with antifouling issues for the last decade, and we will give you some elevator pitches of a few projects that we are currently running that with the data that we will present that will also feed into the tool that Long will present later, so this HullMASTER tool. And unfortunately, Maria couldn't join today because she's home, but she's working on a project called Getting to the Bottom, the quest for a minimum effective biocide releases. And the main aim here is basically to investigate what is the minimum release rate of, for instance, copper or other biocides needed in order to prevent macrofouling. And that is, of course, of interest for a lot of different stakeholders, including paint formulators. And I will show you some preliminary results, but her main research question here is then what I mentioned is what is the minimum necessary dose of different antifouling biocides to prevent marine fouling in European waters. And the results is then, of course, relevant both for the shipping and the leisure boat sector. And what she's doing and what I also have been involved in during the last decade is to detect different biocides by using X-ray fluorescence techniques. So we have a handheld X-ray instrument here at our unit, and Maria is also collaborating with others. They're using this benchtop instrument instead. And her biocides of interest, you see them here to the left. And she's running experiments both on short-term and long-term time. So hence that it could be relevant both for the leisure boat sector and for the shipping sector. And this is conducted in European coastal waters. And regarding the results, what you have been seeing is that the minimum effective dose of copper is 7 microgram per square centimeter in 3 different locations, so both in Sweden, Denmark, and in France. So that is something that is very interesting, and she will continue doing similar work for the other biocides. This data is just about to be published. It has been accepted for publication, so look out for this in the Progress in Organic Coatings if you want to learn more about it. Okay. Then we have Emily, Lena, or yeah, okay.
Yes.
Or shall I? Or...
I am here.
Yeah. You need to stand here so everybody.
Yes. This project that in short called lignin. I will come back to that. But novel antifouling coating, sustainability assessment of marine antifouling coatings is something that the postdoc Emily that joined us from France in the spring she's mainly working. She's the one that's mainly working this project. And the idea is to do a sustainability assessment of marine antifouling coatings, where she kind of, you can say that she compares coatings that contains biocides with FRC, that stands for foul release coatings of silicone based, and then the new novel thing, the innovative coatings. And bio-inspired coatings, hydrogel and lignin. And lignin is a residual product from the wood industry. So this is a collaboration with Luleå Technical University. And the testing that she does, or the aim is to test then the toxicity together with the efficacy. So they both hopefully will be both efficient but non-toxic. I think that's, if you don't want to add something, Erik.
No.
No. And she has test area that includes, besides the waters around Sweden, meaning the Baltic Sea and the Skagerrak-Kattegatt area, also 2 stations in the Mediterranean, so in Trieste, Italy, and Bayonne, France, with the aim to include different salinities. You can see it's a span from 7 to 38. There is monthly monitoring where we have photos sent to us of the frames that you can see, and we then follow how the growth of fouling organisms develop on the different panels with different paint, different treatments. And they are taken monthly, and if I recall correct, they started in spring and they will be terminated now by the end of the year, so they capture the growth season, the fouling season. And then she tests if they are toxic by producing leachate, which is water where the paint has been, and then this is tested on several study organisms on different trophic levels, meaning that they come from different roots, and there are algae, red algae, that I think Jonas Gustafsson recall is red algae. Isn't that true? You've been working with that one. And Nitocra, which is typical test for larval species, and also larvae from the sea urchin and bacteria. So this will then give the results will tell if they are toxic for the environment, and everything will be used in the sustainability assessment. So we move on to the project called Vector, and I leave over to Paulina.
Yes. So I'm Paulina. I'm visible. And I have a background in marine biology, and I'm now doing my PhD in the Vector project. And this is a project that we do here at HullMASTER, but we also work with the Gothenburg University and the biology lab that we have here at GmbL. And basically what we try to do is we monitor invasive species and try to have some sort of pre-warning system in the end, and try to reduce a little bit the problem that comes from invasive species that come. So, as we can see here on the map, that is very old, that's from 2008, but harmful invasive species are a problem basically everywhere in the world. And if you consider that this is only in 2008 and we have ocean warming and we have increased traffic and acidification, which all increases the risk of invasion, this map would nowadays, with actual data from nowadays, would look way worse. So we would have more red and more orange in there. And the problem with invasive species is basically if they're there once and established, it's really hard to get rid of them. So if you have like a few individuals, you can like stop the vector of them coming in, or you can like catch them and eliminate them. If there's thousands of them, it's really hard to get rid of them. And even if so, the ecosystem is altered, and it's not a given that it's snapping back into its original state once the species is. So the best thing to do is basically catch them when they arrive, or even before they arrive. And if we look at how they arrive, shipping is actually like a big vector for arrival of invasive species, and it would be good to reduce that a little bit. So what we do is basically we try to identify high-risk ports with AIS data and distribution maps of invasive species. So for example, if we have a jellyfish that is in the UK but not in Sweden, and we have traffic in between these places and the conditions here are favorable for the jellyfish, there is a certain risk that this jellyfish will come here and conveyed. And then we monitor the reports for our model species and try to develop in the grand scope like a pre-warning system and to have that. The second thing that we do is we look how our species are traveling. So basically not all species travel or attach the same on different foulings, antifouling paintings, or on the same areas of the ship. For example, like adult crabs are not very common on hull fouling, but we can have them in niche areas like sea chests. And another example is we have the sea vomit that, for example, likes to travel on pontoon-like structures, so something that's flat and towed rather slowly. So they can only invade it with towed jetties. And if we know things like that, it's very easy to have like a very targeted and effective measure against this. So that's what we try to do.
Yeah, and the sea vomit, for those that are not familiar with it, it's what in Swedish is called the filsjöpung.
Yeah.
And it is also sometimes called the carpet sea squid. I think it's a colony of sea squids. I think it was the translated
Spya.
Spya was
Yeah.
the Norwegian name,
Yeah.
but it's
We
but it is,
call it something.
yeah.
Hello, everyone. My name is Pei, and I'm also a PhD student. I joined the group early this year. And what I'm doing here is, as you can see here in the title, Hazard and Sustainability Assessment of Commercial Antifouling Coatings. And the abbreviation is for the Swedish. So first, in order to do the assessment, my project is set up, split into 3 different tasks. The first one is to screen all the potential toxic compounds that might release from antifouling coatings. That includes biocide, of course, which is how fouling organisms are killed. And there are also microplastic or persistent substances. And then the next step is to evaluate the efficacy of all the coating system. And then together, combining the result from the 2 tasks, I'm going to do a holistic assessment of different coating systems with the HullMASTER project that you're going to hear about. And currently, I'm working on the first and a little bit of the second tasks. And then here's the result I have. So for the coating system, we have about 190 products that I went through. For the shipping sector, we have 97 products, and 73% of them are copper coatings. And for yacht product sector, we have 93 products, and 81 of them are copper coatings. And for the non-biocidal coatings, unfortunately, we only have 17% and 13% respectively, in both shipping and yacht sector. And here's some results I got from the chemical screening. For the biocides, copper is obviously the dominating type. And in both shipping and the yacht sector. And for all the co-biocides, perithium is the most frequently used biocide in both shipping and yacht sector. And it's not shown in this graph, but DNF actually has the highest average concentration of all the co-biocides in both sectors. I have found 158 chemicals in the coating formulations, but only 8 of them are biocide, and there are 150 left. And then what I'm doing right now is going through all the rest of the chemicals and then do a hazard assessment of the mixture from different types of coating. And then, as I mentioned earlier, I'm going to do efficacy evaluation, which is to field test, coat the panels and put them in the field. This is planned for the next spring. And then at the end, using HullMASTER tool, we're going to do a holistic assessment, combining emission and efficacy of all the available coatings in the market. Thank you. That's all.
Yes, because I already revealed that I'm not a chemist. So what is biocide and toxic chemicals are sometimes same thing. So what is the difference?
So biocides is obviously toxic. It's how the antifouling coating work, which is used biocides to kill all the chemicals, but there are all the fouling organisms. But there might be some additives or preservatives or PFAS, silicone oil that also really toxic to the marine environment that's been added to the coating formulations.
Yes.
So that is the other toxic
that
chemicals.
is clear now. So those are the dedicated to do the work in the paint biocides. Okay, great, thank you.
Right, can I start? Yes, hello
Please,
everybody.
Young.
Yes, my name is Young Wong Kim. I'm a postdoc working in this antifouling research group at HullMASTER. And in this presentation, I'm going to introduce our project called HullMASTER. To make it simple, our project called HullMASTER, the main objective is to develop and improve the HullMASTER, which is the decision support tool for the sustainable ship's hull maintenance strategies. Well, I think to begin with, I think many of you already know much more about the background of biofouling and antifouling than I do. So I will just skip this slide. But I just would like to highlight the importance of the hull maintenance during the ship operation. They can have a variety of socio and environmental damage impact, such as like the emission of the greenhouse gas to the air, and the release of the biocide, heavy metals, and microplastics, etc., and also introduction of course, like invasive species. So it is very important to find sustainable hull maintenance strategies that can be economical, and also that can, at the same time, can minimize the environmental damage impact. However, like finding a right solution or sustainable hull maintenance strategy is a very challenging and complex task because the cost savings and damage impact can vary significantly depending on the various factors. So that's why in our first project, in the whole project, we have developed a life cycle cost assessment tool that can comprehensively calculate the impact of the biofouling and the many various hull maintenance activities. And I believe that this tool will be of great interest to all the stakeholders, like everyone attending this seminar, right? And then I would like to take this opportunity to thank to the authors or the people who developed this tool in our first project. And then, based on a large number of scientific results and scientific inputs, this HullMASTER can provide ship-specific recommendations for the sustainable hull maintenance practices compared to the business as usual scenario or the baseline scenario that you have selected. When it comes to the hull maintenance strategy here, means like the selection of the coating types or selection of the dry docking cover, or the type of the inventory cleaning and the intensity, etc., etc. And then, as you can guess from our project name, HullMASTER, which is the follow-up research project, and then the main aim of this project is to expand our scope of the tool from the Baltic Sea region to the European Sea scale. So we have been conducting a lot of field tests in the 7 different European port terminals in collaboration with the shipping companies like TFDS. And then we also have included like almost more than six commercial coating products with the help of the paint company, so that we can increase the accuracy and the reliability of our tool in the end. Well, This slide shows almost all the research projects in our anti-fouling research group. And as I mentioned, the whole tool or HullMASTER is interconnected to all of these projects. So which means this whole HullMASTER is very comprehensive tool, so that it uses all the scientific results and scientific inputs from this project. For example, like novel coatings or the toxic risk assessments and the inputs regarding biosecurity and emission from antifouling coating and external costs, etc. So as you can see, we are collaborating with many partners to improve our tool in that. So in the later presentation, I will talk more about the HullMASTER and its demonstration. So if you are interested, you can scan this QR code to access to HullMASTER in advance. But maybe you don't have to hurry because I will cover this part in the later presentation. So yeah, thank you.
Yes, thank you, Yong. And we have talked until now about the effort from our side, but again, and I think the title here really captures it very well, that we would not be able to do this without the input from the coating companies, from the shipping companies, and also our team. So it's really, yeah, we need input, and with that hope to develop it to be more useful and used.
Okay, so now we are in the last block before coffee break. So I think we're a little bit ahead in time, so maybe we will have some time for questions. Let's see, depends on the three presenters that come up now, me included. So I will start, and then Mikael Andersen from Valencia is joining. He's not typically in Valencia, but at the moment he is, otherwise he's at Rice. And then Anne will be the presentation as well. So we are doing a lot of applied research, and we very often get requests from different policymakers or different national authorities regarding projects that could help their work in terms of policy making. So that includes the Swedish Agency for Marine and Water Management, which is present here, and also the Swedish Transport Agency. So I will go through some data that's primarily been funded by the SWAM agencies, the Swedish Agency for Water Management, and it covers copper and also the work conducted by an organization called HELCOM. So as Yang Rong mentioned previously, the HullMASTER tool is developed for the Baltic Sea region, and most of our, at least previous research, has been focusing on this area. And the reason for that is that the Baltic Sea is recognized as one of the most polluted sea areas in the world. So it's of interest to understand what sector that are causing this pollution, and also how we can implement measures to reduce that. And in this figure, which is very red, this is something called an integrated status assessment regarding contaminants that was conducted by HELCOM and their work in HOLAS, or Holistic Assessment 3. And you see that almost all the areas here are either moderate or bad in terms of their environmental status. And the reason for that is mainly that the Baltic Sea region has a very large catchment area. We have a semi-enclosed character, meaning that the water exchange capacity is very low. It takes about 20 years until the water is being exchanged. So that means that everything that's being dumped in the Baltic Sea typically stays there as well. So therefore we have higher concentration of hazardous substances compared to other sea regions. And typical pressures include contaminants, marine litter, introduction of spread of non-indigenous species. So the shipping picture here, it puts potential large pressure on this sensitive environment. And Regarding HELCOM, I'm not going to bore you too much here, but just so you understand a little bit what it is. So it's known as the Helsinki Commission, so the abbreviation is HELCOM. So it's the Baltic Marine Environmental Protection Commission. So that's an intergovernmental organization in the Baltic Sea region, and it contains 10 different contracting parties, so all the member states that has a border towards the Baltic Sea. And one of the main tasks for HELCOM is to provide different recommendations in terms of how to implement different measures to prevent the input of different, for instance, hazardous substances and so on. So at the moment, over 260 HELCOM recommendations has been adopted so far, but it needs to be implemented in the national legislation. And as I mentioned, we have this HELCOM HOLAS 3 holistic assessment that I showed you that was completely red for the hazardous substances. And what is behind these figures is different core indicators, as it's called. And one of those is copper. And that indicator is developed based on concentration of copper in marine sediment. So we from HullMASTER, we were a team working on this for a couple of years to develop this copper indicator to set the threshold value for what the environment can cope with in terms of copper in sediment, and then also compare that with environmental concentrations. And this is how the results look for copper. So you see a small green part over here, otherwise it's completely red, or white, meaning that we don't have enough data. But the take-home message here is that we failed to reach good environmental status in terms of copper and sediment. So the next question that the SWAM agency were interested in is that, okay, so what are then the main contributors of copper to the marine environment? And so we did an extensive literature review on that, and also using our own data. We saw that the main player here is the rivers. We have more than 50% of copper is coming from rivers, mainly natural sources. And then we have a smaller fraction from atmospheric deposition, direct point sources, so that's coastal industries. But for the shipping and leisure boat sector, we see that more than a third of the total input of copper is coming from that part. And to the right, you see it's split down to different emission sources, so scrubber, water, bilge, grain, and sewage, which you can't really see because it's dominated by the antifouling paint. And as Peiyu showed you previously, when she went through the European market, copper is dominating in terms of main biocide and antifouling coatings. So roughly a third of the total input of copper is coming from antifouling. So with this information, there was some discussion then at HELCOM level on, okay, can we reduce the input of copper in order to increase the environmental status? And what they came to the conclusion through something called the Baltic Sea Action Plan, which provide measures, is to minimize the release of biocides from antifouling products to the marine environment, and preferably by 2027, replace the use of biocidal antifouling products with biocide-free alternatives on structure, etc., and recreational craft. So this is what was done, the recommendation by HELCOM, and it's now being discussed how it could be implemented in national legislation. So in Sweden, the SWAM agency has handled this together with a bunch of other national authorities. And this measure will be conducted through 7 different activities. I included 2 of those here. One is to propose new guidance documents on EU level on how to perform an assessment of efficacy and excess toxicity of antifouling coatings for the leisure boat sector. And the second one is to investigate if it's justified to introduce an actual ban on the sale of biocidal antifouling coatings for leisure boat imports. So this is one way on how how our research has been commissioned by agencies and how they implement policies. Okay, so with that, I'll spoke
Mikael is present here.
And meanwhile, Mikael is preparing. I just wanted to step in. Of course, we have a Swedish perspective. We do our research in Sweden. Erik presented the Helcom area, the Baltic Sea area. But me, born and raised at the West Coast, also want to a little bit take up that Sweden is a really good place to conduct this type of research when you want different salinities. As we have it, both the brackish Baltic Sea and we have the fully saline North Sea coming in, and that is called the OSPAR area, the North Sea area, the Helcom area is the Baltic Sea area, and exemplified with how we can work with the regional measures, but at the same time, in the shipping business, we have the IMO regulations, that is the global and the strict ones that we also provide information to. Okay. Mikael, are you?
Ska du köra?
I think
I'm
I'm
here.
Yeah, excellent, Mikael. So you just let me know and I will change the next slide and so on.
Yes, of course. Okay, my name is Michael Lea Andersen. I work for, well, I've been working for SSPA for many years, and which are now part of RISE. I'm sorry I couldn't be there physically today, but as Erik said, I'm away on a meeting in Spain. So today I will say a few words about the skin friction database and some recent results relating to the skin friction database. The skin friction database is as many of you I know, I assume, is not a new development, but it's being used continuously, and we still think it's very useful. Next slide, please. So the reason for the skin friction database is that there really is no empirical relation between roughness on vessels or any surface with flow on it. So you really need laboratory measurements on rough surfaces and to measure the skin friction. So we have done a lot of measurements on a large flat plate for various rough surfaces relevant for the marine industry, and we have put all those results into a database where you can extract the result quite easily, I think, at least. We also use this database in connection with CFD for more accurate predictions of increase in hull resistance due to rough surfaces. Next slide, please. So this is the basis of the database or the measurement equipment. It doesn't have to be a flat plate, but it's the most accurate and the kind of measurement equipment that requires the least extrapolation to a full scale vessel. So what we use is a 7 meter long flat plate. It's 1 meter tall with a draft of 90 centimeters. So it's a surface piercing plate, as you can see in the picture. We apply different rough surfaces on it and tow it through our towing tank in our facility in Gothenburg at various speeds between 0.5 and 5 meters per second. So we get a very high, at least for a laboratory, a very high Reynolds number. Next slide, please. So as I said, we have tested a large or big variety of different rough surfaces, different aspects of rough surfaces. Obviously, we have some newly applied coatings. We don't have many of those because we don't think they're very interesting. They all kind of show between, say, 2 to 3% increase in skin friction above hydraulically smooth. Where the real issue is in the marine industry is when the coatings or the surfaces get more rough than a newly applied coating, because then you can easily see 10, 20, 40% increase in skin friction. So for that reason, we tested or tried to test paint damage and repair artificially. We have poorly applied paints kind of to simulate several applications of coatings, which is seen often in the marine industry. We have tested biofouling by putting the plate in the ocean. And we also have some cleaning of the plate. Next slide, please. So this is a picture or screenshot of the actual interactive database, which is available free of charge. You can see the link in the bottom left side. But just to give you a very short overview of what you can do in here, the top curves is, or rather the curves with dots on it, is the actual laboratory or flat plate measurements. You can see that the lines extends in Reynolds number beyond the laboratory measurements. So we use Granville similarity and Grigson extrapolation to be able to extrapolate the results to full scale. You can actually change the length and the speed and the viscosity also of the vessels on the top line, and the extrapolation will be recalculated by the tool. In the middle, you have data selection. You can choose what kind of surfaces you want to look at and kind of sort them. And on the right, you see right middle. You see the rough surfaces that you have chosen. You can also click these and get more information about them. You can get a weighted average. Say if you have 30% light biofouling and 70% newly applied coating, for example, you will get a weighted average in the bottom part. So the bottom part is a quite simple tool using ITTC. If you know the power and the specific fuel oil consumption of your vessel, you can put that in, and you can compare how much the specific fuel oil consumption changes depending on what surface the ship has. So it can be used as it is. We use it a lot for CFD validation and for reverse engineering using CFD. So we can do CFD computations of the flat plate, compare that to the measured results, and by doing that we can get the CFD related KS or roughness value, and then we can get a much better simulation of the flow over a real ship and its effect on wake and propulsive efficiency also. Next slide, please. So as I said, I will talk about a little bit about the skin friction database, but also some recent results from another project called New Skin. These measurements were completed just a month ago, so they haven't yet been included in the database, but they will be. So we tested one quite interesting kind of surface. It's called riblets. If you don't know what it is, it's kind of a sawtoothed surface with about 100 micron in roughness height. So it's kind of a triangular shape, aligned in the flow direction. So the ridges of the triangles is aligned in the flow direction. And this kind of surface has been known for quite a long time, actually, to be able to reduce the skin friction below hydraulically smooth. And we tested this. Maybe you can see on this the left picture is the or it's part of the plate. You can see it has been coated with an antifouling coating. And on top of this, patches of riblet surfaces has been glued on this coating. Next slide, please. Yeah, this is the unfiltered results. We can skip this one actually. So this is the filtered results showing only the skin friction. And what you see here, the blue line is the hydraulically smooth reference measurement. So we polish the plate to hydraulically smooth and do a measurement. The yellow one is the antifouling coating, so it's about 3% higher than the hydraulically smooth as expected. But then the red one is the interesting one because that's the riblet surface, and it's about 3 to 5% lower than hydraulically smooth. But more relevant comparison is to the newly applied coating, so the yellow one, and that is 7 to 9% lower than what you would normally see on a newly built vessel. And depending on type of vessel, of course, that would equate to maybe 5 to 6% reduction in total resistance. So all is good, problem solved, right? Not quite, I'm afraid. Next slide, please. Because we also put this plate in the ocean at the Marine Center near Strømstorps for about 4 weeks. And you can see how the plate looked after we took it up. And you can see there's quite heavy fouling. Unfortunately, we had hoped that the riblet surface would be kind of a repellent for these barnacles to settle, but it doesn't seem to be the case. That there might be some indication that they don't like it too much, because perhaps you can see that the barnacles tend to mostly settle in the small gaps between each patch where there isn't any riblets. It also seems that the attachment strength just by feel and touch seems to be a little bit lower than on the part that doesn't have riblets. But certainly some kind of solution need to be found to have this surface to have better antifouling characteristics. I'm not quite sure how. Next slide, please. And this is the result. So you can see the antifouling coating, the hydraulically smooth, and the riblet surface, the free curves in the bottom, and what we don't want to see is the black one in top, where you can see a very significant increase in skin friction. Okay, I think that was my last slide. Thank you for your attention.
Great, thank you very much, Mikael. So, Ann, I think you're up now,
Yes.
and then I think we will have some time for questions.
Hi everyone, I'm Ann Larsson. I'm based at Tjärnö Marine Laboratory, belonging to the University of Gothenburg, outside of Strömstad. And I was doing my PhD there with Lena. Yes. So I'm into marine ecology, interested in biohydrodynamics, flow effects of marine organisms. My PhD was on barnacles and barnacle larvae, while Lena was working with algae. Yes. So I will just tell a bit of what we can do with our equipment at Tjärnö. Okay, so I can here. Okay. So our experimental equipment that we have is one recirculating flow channel, and it's 7 meters long, so we can have a fully developed boundary layer for the test section. But it's 0.5 meters wide and 30 centimeters high. But we can't run it more than 1 meter per second, so it's not high speed flow. But we can control the flow very controlled. Know what we have. And we have some different equipment. So we have plastic Doppler velocimeter. This is the old one. But we have a new one that also can do profiles. Sure. These 3 centimeter stretch, high resolution, about 10 measurements for this. And it's one that is made to work in flume. So, yeah, not too much sound. Outdoor ones are much more powerful. But then we also have this equipment with a laser and a camera that we can use then for particle image velocimetry and laser-induced fluorescence. So with particle image velocimetry, you put particles in the water and you illuminate with a sheet from the laser. And then you look straight into the laser sheet with the camera. And then the machinery is tracking the particles, or the software is tracking the particles. And you can have very high resolution, both in time and space. So 15 measurements per second. And the resolution in space is how much you are zoomed in with the camera. So I will show you later some very high resolution. This is just an example. So every vector here is one measurement. And this is actually average. Kind of salmon. So this is the other method that you can also use this laser camera with. Laser-induced fluorescence, and then you use a fluorescent dye to mimic a chemical release, maybe a scent release from an organism. Use it also, we are mimicking sperm release from corals, for example. And that's because the majority of the dissolution or spread of the chemical is due to the turbulence, so much about the diffusivity when it comes to. So you can mimic what's happening by using this fluorescent dye. So when you know what the solution is to start with, the concentration of the solution to start, you will have a relative measurement and you will know how much the concentration is. So this is in all of these, each pixels, you can have a concentration compared to the source concentration, and then you will know how spread it is. It's used for look at reducing bond layers. Yeah. So here I'm going to show a bit more what we have done that has to do with fouling and fouling paints. And we can look at boundary layer dynamics then using particle image velocimetry. And we have used it, look at the panel in the flow here. This was quite a short panel, but anyway. And here is some barnacles in the panel. We have sprayed everything black because we don't want the reflections from the laser sheet. So then you can compare what is happening to the boundary layer when you have the roughness. And here we have used also some standard thin, smooth, different widths, falling coatings, barnacles. So you can look at roughness effects, skin friction coefficients. Of course, the longer you make this panel with fouling or the grit, the better and more relevant results. Okay. So I told you that you can have very high resolution using this PIV. And here we have zoomed in, so we just see 4 × 4 millimeters. So it gives us 5 vectors per second. So here is the flume floor. It's a slate flume floor in this case. This is just 4 millimeters above the flume floor. So this is an average 20 centimeters per second. Quite low speed compared to ship hull, of course. But also to show you that you can actually see this very dynamic environment. So here we slowed the things down 7 times so you can see what is happening. Because you can have the notion that, oh, it's quite calm down here. But you can see that they are regularly coming in sweeps of higher flow velocity. That is penetrating quite deep into the lowest part of the bond. So it's very good if you want to study things in detail, this equipment. Yeah, so for example, what we have used these measurements is to look at the thickness of the viscous sublayer. The diffusion boundary layer, they are, quite the same. So with free stream velocity here, we can see that the thickness of the viscous sublayer is decreasing. So it's flume floor in our flow chart. And this is, of course, relevant for the leakage of materials from paints and coatings that will depend on this boundary layer. And here we can also see using laser-induced fluorescence instead. Here we have a piece of wood that has been drowned with this fluorescent dye. And this is just a very, very low flow speed of just 1 millimeter per second. That's illuminated from above, and you can see that this over-separated part here is actually this diffusive boundary layer. Here we can see, and we have tried to do it also in higher flow speeds. You have the right, you need to have a very, very slate surface for things to diffuse out of. But it can also be used to look at the diffusive boundary layer. Too long? Okay. So what we have also done is to look at factors affecting release rates of antifouling, from antifouling paints using XRF before and after. And we can also chill the water to about 5 degrees. So we have a cooler, so we can control the water. And the salinity is what it is when it comes from outdoors. Yeah, around 30, 32. Deep water. So what's been interesting is to compare a hard copper paint, polishing copper paint, and to expose them to different flows and look at how the thickness of the diffusive boundary layer and also shear stress is affecting the release rates. Biocides. And especially to compare what is important for these different things. It's interesting. We would like a coating that is releasing material when they are in harbor, but not releasing more when the ship is running, because that is just not necessary. So that is why that is interesting. And together with the Danish Technical University, we have also looked at flume exposure compared to rotary immersion using the same coating length here in the flume, and then compared to rotary immersion. But we don't have the answers yet on it. Yeah, it's also interesting to look at difference in upstream and downstream panels, because you can imagine that further downstream, the thicker or the more material is coming into the diffusing bunker layer, affecting the release. Yes. That's it. Thanks for listening.
Thank you.
Should have given all of them. Thank you so much.
We can have it. We can do it like this. So we have I think we have like 10 minutes at least until we have a scheduled coffee break, right? So there are questions. I think also those. Maybe we can start with you that managed to come here to Gothenburg.
Or comments.
Or comments. Yeah.
Sorry, I have a question. It's Heather from Lloyd's Register. I don't know, can everyone hear me?
Yes.
Oh, excellent. That's great. Thank you so much for that fantastic set of slides so far. It's really, really interesting. I'm so glad you invited me to join. Early on in the slide decks, we were talking about materials and specifics with chemistries. Obviously, it's a step change in the market. We've recently developed a product which is helping ship owners to choose antifoulings in terms of their, being able to clean these things. But one of the questions that keeps coming up is the perception of foul release coatings being more environmentally friendly than biocidal. And I heard you, and we've been looking a lot at PFAS as well as Lloyd's. So you mentioned silicone oils and PFAS, and I wondered if you could perhaps give me a little bit more information about the work that's been done around that area, because I'd be super interested in hearing about it.
Yeah, thank you. Can you want to
Yes,
come up?
yeah, well, that's my question.
They come here so they hear you.
First of all, thanks a lot for your question, but unfortunately, I am still in the stage where I'm looking at all those chemicals, so I don't have any thing about that.
We can maybe mention that Maria Lagerström couldn't join us now, so she took the lead on one study. We were also included on that one, where we did an overview of the scientific knowledge regarding impacts of foul release coating compared to traditional biocidal coatings, and the data that we summarized, which were primarily these that you produce leachate water from the different coating types, and then you assess what kind of adverse effect it can have on non-target organisms. Then we saw that the traditional biocidal coating were by far more toxic. But of course, that depends on the test species and endpoints that you have included in the study, etc. So there may still be some issues here that is one of your main research question, and you started when is it 10 months ago or something? Yeah.
Yeah, but I'm definitely going to look at that later.
Oh, excellent.
Yeah.
I mean, I'd be interested in keeping in touch if that's okay, and not the right forum, but just to explain a little bit more about what we're trying to do here. I used to work for a big paint company for most of my life, so paint's all like close to, and it's interesting what's happening. So if there's anything we can do to collaborate, I'd be really interested in that. And thank you very much for fielding my question.
Yeah, thank you very much, and we will definitely get back to you. Thank you.
Yes.
Do we have any other questions?
I see a very elaborate question for me in the chat.
Oh yeah.
From who was it? Andrea from Hempel, right?
Yeah, that's true. Or Andrea, maybe if you can, if you are able to just maybe summarize that question a little bit, please.
Otherwise, I can summarize it from what Andrea has written. It's a very good question, actually. And it is true what you write that you can't.
Could you read it again? Because we can't see the
Can
question. Could you read it?
No. Reread it. Yeah, it's long.
No, yeah.
It's long, okay. But
Mikael, if you,
Mikael has
yeah.
captured the question in the question.
Yeah. So the question, as I understand it, it's a question of the extrapolation, obviously, and that using the Granville similarity law will not necessarily get you to full-scale Reynolds number, and that's absolutely true. So to answer your question, Andrea, we use kind of a two-step method, or we extrapolate in if I can use the term, two dimensions. One is the length, and one is the speed. So we use the Granville similarity to extrapolate in the length dimension. So obviously the plate is not the full scale length of a vessel. It's 7 meters. So as I said, we use the Granville similarity to extrapolate in the length dimension, and then the speed is also not often, at least, full scale speed. We have a maximum measurement speed of 5 meters per second with the flat plate, but then we use the Grigson extrapolation to extrapolate in the velocity dimension. So using those two together, we can get to the full scale, not only the full scale Reynolds number, but the correct combination of length and speed. I don't know if that answers your question, Andrea. There are papers, you can just search for skin friction database in my name. You will get several hits on papers where the method is described in more detail. I don't, as I said, I'm in Valencia, so I don't have those papers available right here to show you.
Thank you. I hope that helped.
So Andrea, we can't hear you, unfortunately.
You can't hear me?
Yeah, we can hear you, but I see that Andreas is
okay.
Speak, but we can't hear you.
Yeah.
Try again.
Maybe now.
Yeah, now we do. Yeah, please.
Okay. Thank you all for very interesting presentations. I'm really enjoying this seminar. Yeah.
Thank you.
There's another question from.
Yeah, we have another question. It's about my own eyes. It's about hydrogel-based antifouling. What is the current progress in usage for both yachting and shipping sector? Thank you.
Thanks for your question. And I think it's more utilized in the leisure boat sector, but it's not only hydrogel, it's more of a combination of different technology. For example, if it's a silicone-based coating, but with the hydrogel incorporated in it, I believe. And for the shipping, I would say the majority of the coatings are still SPC, ablative coatings. I remember seeing a new product that's using hydrogel, but unfortunately I ended the collection of my data this July, so that's not included in this specific project. Yeah, I'm not sure if that answers your question.
Any more questions?
May I have some?
Yes, please.
Yes, Santiago Arias from Hempela. First of all, very interesting, let's say, all the topics you are working with. I think many of them, will be very interesting to understand the results. Antifouling testing, toxicity of leachate. I think this is a very interesting topic. hazard of different commercial antifouling coatings. I think it would be very, very good. I have one question, but I will say it afterwards on this one. No, the only comment is when I see these maps of copper, let's say toxicity and in the sediments, I think I explained already 1 year ago in the conference in Gothenburg, we have solutions already, technical solutions. Now it's up to the legislator to legislate, like Finland, for instance, has done, meaning that if the legislation push, the paint companies will move on. I think there are solutions available in the market. I think this is very interesting. One question about this sustainability assessment. You are talking about measuring microplastics. Are you trying to measure release of microplastics from different types of coatings?
Yeah, that's the plan, but it's really difficult to measure microplastic. You can't measure it with the same methodology or, oh, sorry. Okay. So, hi there. To measure microplastic, it depends on what you want to look at. If you want to look at the number of the particles, or if you want to look at the weight concentration of the plastic, that require different set of analytical technologies. And it's even harder if you have like a paint flake with copper on it or other substances. So we're still exploring different way and how to better incorporate it within our project, within what we want. So yeah, that's part of the plan, but I'm still looking into that.
Thank you.
It would be really good if we can measure microplastic.
And thank you. And one of the questions about hydrogels. Hydrogels are used both in marine and yacht coating at the moment. So this is for you to know.
Thank you. Thanks so much.
Okay, I think the clock just turned 10:20, so let's go for a coffee break and we'll be back at 35, yeah. Okay, thank you.
Not close to my computer.
All right, thank you, Eric. Okay, let's dive into what her master is and what are the core modules included in her master. So in this seminar, we'll try to be informative about our research output or about her master. But I will not cover everything because of the limited time. So as I mentioned earlier, if you look at the right side, so her master takes ship-specific information, such as the ship's design characteristics or operation profile, and the sailing region, etc., etc. So all the specific information. And then in the end, if you look at the last stage, we can, by using this tool, we can calculate the cost for the operators, society, and environment based on your selected her maintenance strategy. And to make it possible, as you can see, there are many steps in between. And to make it possible, of course, there are like main modules in her master. So throughout this presentation, first I will introduce what are the core modules are and how it is composed of. So the first module is about biofouling growth model. So this module estimates the biofouling growing trend on the Earth, depending on the coating types or depending on the environmental conditions where the ship is sailing. And the second module is the ship performance and energy penalty module. So as you can guess, this module estimates the impacts of biofouling on the ship's hydrodynamic performance, like the drag changes due to the biofouling and her maintenance events. And the third module is to estimate the emissions to water and air, and which will provide the emissions to the marine and atmospheric environment due to the hull coating application or due to the maintenance activities. And the last module enables us to calculate the cost-benefit analysis. So it will provide the economic gains and the socio-environmental damage costs of the selected hull maintenance strategy. So to make these core modules, of course, we are using a wide and a variety of inputs for the scientific result. For example, of course, antifouling efficacy test result and the X-ray measurement to estimate the biocide emissions from the antifouling coating and the ship performance estimation and various price estimates from the industry. And of course, we are using many supporting research and scientific results. This slide shows two different types of version of the HullMASTER. So I would like to highlight that the current version, which is available online on our China website, is our earlier version, which is focused on the Baltics region. And then now we are actively working on the next version for the European sea scale. So in the next version, there will be more experimental data and more options and more scientific results will be included. So from now on, I will talk more in detail about each module. Yes. And then, if you can see this slide, like in our first project, we have conducted a static immersion test at 3 locations on the Swedish coastline. So as you can see here, these 3 points, we have conducted our static immersion test from our initial project, And then now we are going to expand it to the European sea scale, right? So as you can see, there are like locations from Gothenburg, Immingham, Groningen, Kent, Copenhagen, Trieste, and Pandy are included. So by doing this, it allows us to cover like wider range and various environmental water conditions in the European waters. And then this slide shows our experimental setup. As you can see, we have used different panels with a different coating applied. And then these panels were attached to the frame. And this frame was submerged into the water, like at least 1 meter below the water line. And then this frame was positioned to minimize the impact of the water flow, so that we do not want to include any impact from the water flow other than the other effects. So if you look at the right side, this is the picture took from the Gothenburg terminal, and here, maybe around maybe here, the frames are installed, and then we took out this frame like every month and to check how the fouling conditions on each panel, depending on the coating type and depending on the environmental conditions from the other locations as well. And we have categorized our coating type into 4 different categories, like biocide-free inert coating, and the biocide antifouling copper coating, and the foul release coating, but which contains the biocide in the coating. And the last one is biocide-free foul release coating. And then even in this category, there are some commercial coating products from 6 different products. As you can see, like there are 2 products and 2 products for foul release coating. And then over the 12 months emergent static, we have, as I mentioned, we have monitored the panel condition every month, which means now we have more than, I think, 2,500 totals of each of this kind of panel. And then we have monitored each panel. So if you look at this result, it is the result after 12 months static immersion. As you can see for the control coding on the top row, you can see that their fouling intensity quite varies depending on the region, right? Like the tree aspect, Pandy, and Gothenburg, they have like barnacles and very hard foulings covered all of the surface. While the Kent, Immingham, Blardingham, like relatively, they don't have much fouling. So you can see fouling intensity quite varies depending on the region, even in European waters. And if you look at the below coating types, like the anti-fouling coatings and the foul release coatings, they are working quite well compared to the control coating, right? They don't have that much fouling, mostly some biofouling or very soft fouling types, even after 12 months immersion. And then, well, of course, their performance varies slightly different depending on the region and depending on the coating type. But it is challenging to say that which coating is better, significantly better, or outperform than the other coating, because as you can see, they are like more or less very similar, and even like for example, from the anti-fouling copper coating, as I mentioned, they have two products, and then depending on the commercial products, their performance also slightly vary. So maybe in this context, we need more investigation regarding anti-fouling efficacy test results. And then, based on our collected photos, we have visually inspected the condition of the fouling on the surface of the coated panel. And we calculate the fouling rating based on the NSTM fouling rating, which is provided by the US Navy. So the main factors to calculate the fouling rating here are the coverage of the fouling on the surface, like how many percentage are covered by the biofouling. And another one is degree of the fouling, whether it is soft or whether it is hard type of the biofouling. And this slide illustrates the biofouling intensity map in the European waters based on the static emergent tests from our project, as well as published other studies. And this assessment is based on the primary coating, which does not contain any biocide, which means you can see the pure fouling intensity difference for each region. Like the red marker here represents the higher fouling intensity, and the green marker represents the lower fouling intensity. So as you can see, they have a really different fouling intensity, even in Europe. And like Mediterranean and the Atlantic Ocean, mostly they have red markers, which means they have quite high fouling intensity. Conversely, if you look at the Baltic Sea, as Lena and Eric mentioned earlier, like they have quite different salinity gradients, and you can see that there are many like yellow, orange, and green colors, which means relatively less intense than the other region. So from this, based on our finding, we got to know that, okay, what is the main factors affecting the fouling intensity in Europe, or how we develop our fouling growth model. Then first, in our first project, we have used the salinity as our main factor. and then the cumulative idle time per the manufacturer. So if you look at this diagram, it shows the fouling rating over the idle time. And this gray marker represents our field test result. So this one is matches with this the above pictures, right? And then, as I mentioned, we initially used cumulative idle time and salinity as our main factors to model fouling growth. And then this is how we developed in our first project. Of course, there are many other environmental parameters affecting the fouling growth, like even pH, flow speed, light condition, nutrients level, etc., etc. But maybe it was not easy to cover everything for this region. And what we want to do is anyway to get a decent prediction based on the certain parameters. So that's why we have used cumulative idle time and salinity for the first prediction. And then we found that there's a seasonal effect affecting the fouling growth. As you can see in this orange color line, depending on whether it is summertime or depending on whether it is winter time, there's a different fouling growth rate. So we have included the temperature into the manufacturer as well. So this blue line is now converted to this orange colored curve, which follows quite well with our collected data. So this is how we so far modeled our fouling growth in different regions and depending on the different point types. And then we will move on to the second module, ship performance and energy penalty. To estimate the changes in the ship's hydrodynamic performance due to the biofouling and the her maintenance activities, we need to convert our fouling rating scale to the hydraulic roughness scale, referred to as KS in micron, because fouling condition is just talking about whether we have severe fouling or soft fouling, that's all. And then what we want to know in the end is the frictional drag increase of the ship, so that we need to convert our scale to the hydraulic roughness scale. And also, as you can see in this table, we have used some data regarding the initial her roughness condition after her maintenance event. Which means if you look at this green box, depending on her maintenance activities, her roughness can vary. So for example, if we are applying the new foul release coating on her surface, then the average her roughness value can be around 15 in KS micron. But if we are applying the in-water her cleaning with the moderate paint wear, then in this case, probably our average her roughness can be around 80 microns in KS. So that's how we model different her maintenance events in our tool. And these are based on the many different relevant sources from the experimental data and the CFD and the published papers. And then, as there have been already some discussion about like gramless similarity scaling, etc. But anyway, in this tool, we are using KS value, which is her roughness, and then in the end, we want to know what is the friction drag of the ship at a certain speed. So we are using gramless similarity load scaling to estimate, in the end, to estimate the percussion power penalty of our ship. So as you can see here, like this curve is the smoother case, speed versus power. And then depending on our her roughness condition, in the end, we can estimate another curve, speed versus power, so that we can get to know what is the power penalty. This discrepancy will be the power penalty at the given the ship's speed. And then regarding our validation of our tool, especially for the biofouling growth and the ship performance module, we have used 9 ships operational data, and which is equivalent to almost 40 years operation data. And then, as you can see here, well, it is already published result, but this difference between the prediction and the onboard measurement was almost like plus minus 4 percentage points different for average value. So I think it is quite a good agreement. Even from this kind of tool, we can predict very accurate results compared to the onboard measurement. And if you look at the right side, the right curve, right graph is the ship's power penalty according to the ship's operation time, depending on the different her maintenance events. So the blue curve here, this one represents our prediction, and the gray dots represent the operational data, ship's operational data. So you can see that this curve follows quite well according to the different her maintenance and maybe changing the coating type as well. So based on this, I would say so far our tool is quite good. And then in addition to that, we are trying to add more validation cases that the ship is selling in the European goods based on our current project. And then the third module is about the emissions to water and air. I think most of you are interested in this part, not the other, the first and second part maybe. But this slide is illustrates the different phases in the lifetime of the her coating, like starting from the application of her coating to the complete removal of the paint per coating at the dry dock. And if you look at the ship's operational pace, you can see that there is air emissions due to the energy penalty. And then also there's a emission to water due to the energy penalty from if the ship has used a scrubber, then there's a scrubber effect. And also, of course, the emission from the antifouling paints in the water. And during the her maintenance phase, if ship has applied in water her cleaning, then of course there's emissions from the antifouling paint. That is obvious. And the items that are written in gray color, we haven't included them in our tool yet, but of course we are trying to update our tool in the future further. So this slide shows the release rate of copper and zinc from antifouling coating when the ship is submerged and sailing condition. And it is modeled based on our previous static immersion tests. And then we measured the heavy metal contents on the coated panel between 1 to 14 days and 14 to 56 days after immersion. And then based on this data set, we have modeled our release rate of copper and zinc, as you can see on the right side. And this model is based on the data set from 4 different locations. So we have used 4 different salinity as our variable in this model. But for the longer term changes of the release rate, we have additionally considered the decrease ratio that is obtained by the other published studies. So they are all based on our previous project result. And then now we are trying to include more extract measurements based on our European E-scale tube tests so that we can upgrade our biocide release rate model. And also, as maybe as Anne mentioned before, like we are still also considering to include the ship's biocide release during the dynamic conditions, because our data set is based on the static imaging test. So probably we can consider more effect during the ship's dynamic condition. And then not only the ship's sailing, but also during the ship's our maintenance stage, like during the inverter cleaning. As you know, like there's a paint particle release, and which will also contribute the copper and zinc release from the antifouling coating. And then we have modeled our release rate of copper and zinc into based on our per cleaning intensity, like the low intensity, medium intensity, and the high intensity. And then these inputs are from the previously published papers. So if you look at here, like this is the equation of the release rate from the Sun's paper from Korean research group, and they have estimated release rate by analyzing the effluent samples collected from the actual ships per maintenance. So actually, I recently met the authors of this paper, and then I learned that they're collecting the effluent sample from the actual ship was not easy, practically. So which means there are not that many samples, like 4 or 5 ships, and then which means there may be some uncertainties for this data set. And then also, depending on the her cleaning like method, whether it is diver cleaning or the robot cleaning, or depending on the her cleaning intensity, or even depending on the cleaning company, like their release rate can significantly differ. So based on our finding or our experience, we need more collaboration with the industry to fill this gap or to reduce the uncertainty. And then earlier I mentioned that we in the ship performance module, we estimate the percussion power penalty due to the biofouling and her maintenance activities like this. And then to estimate the emissions to water and air due to the her roughness and maintenance, we are considering the emission factor from IMO greenhouse gas study so that we can estimate various different types of emissions which will affect the climate change impact, human health impact, marine eutrophication, and marine ecotoxicity, etc. So far, we haven't included acidification, but yeah, that is also something to be upgraded someday. And then there's a microplastic. Moving on to the recent issue of MEPC 80, there was a discussion about microplastics release from antifouling coating. And then there were some inputs from Norway, DNB, and they have shown some kind of very simple, approximate way to estimate a microplastic release. If you look at the right side, this is kind of the equation to estimate microplastic release rate. Consider including the wetted surface area and dry film thickness provided by the paint manufacturer, and the microplastic contents in dry coolant, and depletion rate per year. Yeah, so that's how it is. And then we are considering, of course, we need more inputs and more sophisticated data or method, but we are planning to include microplastic release based on this equation during the ship's sailing and during the ship's maintenance phase. And then one of the challenges nowadays is the risk of invasive species, and like marine species can be attached to the hull and the niche areas, and so that it can be spread into the different regions when the ship is operating. Additionally, when the ship is applying the hull maintenance, like the in-water hull cleaning at the port or the dry dock, there can be the marine species can be detached to the local waters, so that there will be the risk of the invasive species. So that has been covered quite. That has been discussed a lot nowadays, right? And then, of course, as you can see, I have written that under development, which means we don't have this yet, but we are expecting to include the biofouling tracking and risk assessment result from the vector project, which Lena and Pauline are working on. So now the last module. This module enables us to calculate the cost-benefit analysis in terms of the ship's operator and in terms of the society, based on the business as usual scenario. So for the operator's cost, as you can see here, there are electricity penalty, bunker penalty, surface treatment, coating, and in-water hull cleaning costs are included. And then for the socio and environmental damage, as I mentioned earlier, there are like health impact, climate change, marine eutrophication, and marine ecotoxicity. But as I mentioned, we haven't included the risk of invasive species and the microplastic release. And it is important to remember that this kind of cost-benefit analysis due to the biofouling and hull maintenance is compared to the hydraulically smooth hull, which means HullMASTER is designed for analyzing the relative cost difference across the different hull maintenance scenarios, rather than providing the absolute cost. So maybe you don't know what is the absolute cost by the biofouling and hull maintenance, etc., because their reference points are all different. But based on this, you can identify which one is better or how much can you save based on the other business as usual scenario. So that's how it works in cost-benefit analysis. And this table shows more detail about our cost contents and the relevant sources. And I think we have made an effort to include the data set or costs from the industry. But it is important to note that this cost-benefit analysis can be different based on how you define the cost or where you get the sources from. Because most of the data set is from the industry, so sometimes there are not that many samples, so that it will increase the uncertainties. Or sometimes there's a large variation depending on the company or depending on the sources. So yeah, it is really important to get more information and data sets from the industry, and so that we can estimate more accurate results when it comes to the cost benefits analysis. So I think I have covered about our core modules briefly, but I don't think it was that brief. But anyway,
Excellent, Jaron. Do you want 1 minute break? I can.
I think maybe there are, if you look at it, there are any questions.
If there are any questions so far, yeah. Otherwise, I have a competition ongoing here, and only you in the room can attend. And the first one that gives the correct answer to what the master in HullMASTER stands for will get a nice prize that I have made from the leftovers in the coffee. That would like to try. I mean, it's not the end of the world if you don't say correct. I can give you the first word maybe. I don't know, you have to correct me with maintenance.
I'm searching one. No.
They were underlined.
Yeah.
Okay, maintenance strategies.
Environmental.
Or
Environmental.
it could be environmental, but it's actually emission.
Oh no. Oh, reduction.
Reduction. I think Andrew, you spelled it out. Okay, so then we leave the floor to Jan. Yeah.
Great. No one.
Are there any questions? Can I ask a question?
Yeah, please.
So when they do hull cleaning, don't they take care of anything? Is it just going out in the sea?
As far as I know, there's a facility on the land to treat, to have the treatment of the collected effluent from the in-water cleaning. But of course, it depends on the hair cleaning company. But I've heard from the authors from some paper who gathered effluent samples, and then they mentioned that sometimes they are just showing the facility, but they don't do the treatment properly sometimes. So according to their release results, like the effluent results were quite different. Like sometimes it can treat, I don't know, efficiency was like 80%, 90%, but sometimes it was 10% or 0. So it's really uncertain. But anyway, there is something that they are doing some filtration and treatment for the collected effluent. Yeah, that's what I know.
Yeah, and we have seen some question, but we will come back to it after this presentation. So we will not. We will.
All right, then we can move to the tutorials on how to use this HullMASTER. So I think this tool is very intuitive, so you can just follow simply according to my explanation, I believe. And HullMASTER is open to the public on our HullMASTER website. So if you search HullMASTER HullMASTER or maybe HullMASTER Antifouling Research Group, I believe you can find this website easily. And then if you access to this site, you can download HullMASTER. And also you can find the instruction and the relevant papers. And then once you download the program, if you open the file, then there are several files included. And once you double-click this HullMASTER icon, you can easily find this user interface. So here I will just show you an example using the 190-meter Ro-Ro vessel sailing in the Kattegat and North Sea. But this is just for the tutorial, so you can just refer to some information, but it is only for one ship case for the tutorial. So if you want to run the simulation first, you have to specify or select your ship information. So you need some inputs like ship's length, draft, displacement, engine specs, perfusion, and also the important thing is that you have to specify your fuel type. But if you don't have this information, there's another option like the road. You can load the default vessel case according to the ship size and according to the ship type. And then you also have to define your vessel's operational profile and environmental conditions of the ports that the ship will enter. So this information includes the ship's average sailing speed between the ports and the time, how much time that the ship will spend at the port, and also the seawater temperature and the seawater salinity of the port. So this information will be very information to estimate the biofouling growth on your berth when the ship is berthing at the port. And then the most important part is to define her maintenance strategy, of course. So here you can specify the interval of your ship's dry docking, and you can set the simulation period, how much time do you want to operate the ship. And you can select her surface treatment at the dry dock, and you can select the coating types. Here we have 3 different coating types so far, like the conventional copper-based biocide coating, and the power-release silicone coating without biocide, and the inert coating with the abrasion resistance. But as the other our members already mentioned, there will be probably some other lower coating types and some more coating included. It will be included in the future update. And then if you are planning to implement the in-water hull cleaning during the ship's operation in your scenario, then you can also select the frequency of your in-water hull cleaning and type of the cleaning approach. And here also you can specify the cleaning trigger option, which means if the ship surface reaches certain level of the fouling, then the cleaning trigger will be activated automatically based on your setting. If, for example, if the power penalty of the ship reaches 50%, then if you take this option, then the cleaning will be automatically applied in this tool. Then, if you have once you have input everything related to your ship operation profile, per maintenance scenario, everything, then you go to the G tab and then press the calculate button to run the simulation. Well, I think it will not take longer than a few seconds to a few minutes, I think, to run the simulation. But depending on your her maintenance scenario, for example, if you are running 25 or 30 years of the operation, and if you have selected many different her maintenance events, like maybe 3 times per in-water cleaning per 3 times per year and everything, then which will probably take, I don't know, 15, 20 minutes or more than that. So it really depends on your setup. But typically it will not take much time. And once you complete the simulation, you will find this useful, valuable result. So if you go to the E tab, you can find the biofouling growth on your hull, depending on the port. And also you can find the perfusion penalty of the ship over the time, depending on her maintenance event. And if you go to the tab D, then you will see the biocide emission trend according to the ship's operation time. So if you have selected your coating type as maybe like copper-based antifouling coating, then you will find this trend according to the time. And then if you go to the G tab in the result part, you will see many different bar charts, which will visualize your like operators cost and socio-environmental damage cost, etc. So first you will find the operators cost part, and you will see the electricity penalty, bunker penalty, like her maintenance cost, and the sum for the operators cost for your selected scenario. And if you have simulated several different scenarios, then you can easily compare the different scenarios in terms of the operator's cost. So if you look at the result, for example, like this red color bunker penalty for the antifouling coating and power release coating, they have much smaller bunker penalty cost compared to the biocide-free inert coating. That is obvious. And then if you look at the yellow part, maintenance of the power release coating, then power release coating has slightly more than the antifouling coating and the biocide-free inert coating. And this case, like because of the high application cost of the power release coating, it is reflected here. So that's how you use the HullMASTER, especially for the operator's cost. And then also there's a societal cost, which means environmental damage part. And similarly, you can also compare many categories of the environmental damage. As I mentioned earlier, like there will be human health impact, climate change, ecotoxic, marine ecotoxicity, and etc. Marine eutrophication, etc. And then finally, you will see this comparison. And as I mentioned, HullMASTER is designed for comparing the different scenarios. So you can see that like you have to have your business as usual scenario on the baseline. That will be your reference point. And then you will see how much you will save or how much you will lose, depending on the scenarios, depending on the like operator's cost, depending on the social environmental cost, or the total cost. So, well, that is all for the tutorial. I hope it was easy to follow. And of course, there are something more to say, but maybe I think it is enough. But if you have any questions regarding how to use HullMASTER, or if you want to contribute to tool development, feel free to reach out to me, or feel free to reach out to our members. So can I continue? Okay. So it will be the last presentation for today's seminar. Anyway, so so far we have looked at using HullMASTER, right? Only for the one ship case in the tutorial. And if you want to know how specific maintenance strategy of your vessel affects the economy and environment, this is how you evaluate it using the HullMASTER. But moving one step ahead, if you want to answer the question, what is the most sustainable ships per maintenance strategy for the specific vessel case? I mean, that is what we want to know, right? In this case, to find a solution, we use the HullMASTER to run the simulation to include as many feasible maintenance scenarios as possible. So here we have used the RoPax vessel operating in the Baltic Sea region, and then we run the HullMASTER to repeatedly simulate the 93 different maintenance scenarios to find the best scenario. So here, when it comes to the best scenario, means like maximizing the economic benefit, at the same time minimizing the environmental damage cost. So that is our goal. And to find the best scenario, we rerun all of the simulation for the specific region. And this result has not yet been published, but I hope you will be able to find more details sooner or later on the journal website. And then here we have used a case of the very typical 190-meter RoPax vessel sailing in the Baltic region. And then we are assuming that ship is operating for around 10 years, using the low sulfur marine gas oil as their main fuel type. And then we have used ships, the actual operational profile, as you can see here. And then we have used the actual ship's operational routes. So it covers like Skagerrak, Kattegat, and Danish Strait, and the Baltic proper region, which means, I mean, of course, it doesn't include everything, but we try to cover Baltic Sea region, I mean, surrounding Baltic region. And then, as I mentioned, we covered as many feasible strategies as we can. So here, total 93 different scenarios were included. And in more detail, as I mentioned, there are 3 prototypes. And then we have considered 3 different dry docking intervals, considering that this ship is RoPax. And then we have covered different in-water hull cleaning intensity and different frequency of the in-water hull cleaning, like 0 time to once per year, twice per year, 3rd time per year, etc. And then for the far release coating, we didn't include in-water hull cleaning according to the paint manufacturer's feedback. So as you can see here, like for the biofouling copper coating and inert part abrasion resistance coatings, they have like 45 scenarios. And then for the far release coating, we couldn't add in-water hull cleaning, so there will be only 3 different scenarios. Total 93 scenarios that we have implemented. And this is kind of results. This slide shows the cumulative cost for the ship's operator and for the society and environment. Well, it looks a bit complex, but I will try to explain this simply. If you look at this chart, the y-axis represents the socio-environmental damage cost saving compared to the baseline scenario. And then the x-axis represents the operator's cost saving compared to the baseline scenario. And then here, baseline scenario represents the worst case of typical antifouling coating that does not include any in-water hull cleaning. So this is kind of the worst case for the typical antifouling coating. And then each sample or each marker represents each per maintenance scenario, which means there are 93 different markers on this plot. So if the marker is located on the right top corner on the first quadrant, which means that will give the largest saving for the operator's cost and for the socio-environmental cost. And here, as you can see that this green marker, which is far release coating, shows the largest saving for the operator and for the society and environment across the different regions in Baltic Sea. And then, as you can see here, like they have quite large deviation, like scattered samples. Based on this, you can know that, like, depending on your per maintenance strategy, the cost saving can vary a lot, even for the operator and even for the society. And for each vessel, they also have different cost saving. That means it can be influenced by the environmental condition of the ship sailing, environmental condition of the sailing region, and also it can be influenced by the ship's operational profile, right? They are all the different factors affecting the cost saving. And then if you are going to apply the best scenario, then based on our results, you can save up to 9.3 million euros for the operator's cost, and you can save 7.9 million euros for the socio-environmental damage cost compared to the baseline scenario for 10 years. So I think it's quite a lot, right? Because even if it is 10 years, but this is only for one ship. Of course, I think nowadays, like the shipping companies are maybe not this baseline, but maybe around this, so that the difference will not be that much. However, we have to find more sustainable and more economic benefit, of course, and more less environmental damage. So that is why we developed this kind of decision support tool. And then if you look at this table, it shows the best scenario for each ship and each coating type, which means this point. And then a common finding from this best scenario is that the higher fouling intensity region requires more frequent hull maintenance, like the more frequent in-water hull cleaning and less dry docking, and shorter dry docking recovery. So, for example, Skagerrak and Kattegat, which has higher fouling intensity than the Baltic proper region. So, if the ship is sailing in the Skagerrak and Kattegat region, then you need more frequent hull maintenance compared to the ships in the Baltic proper region. And I think that will be applied to same for the entire European region. Like as I already shown that the region, each region has different fouling intensity, which means they will have different solution when it comes to the operator's cost and when it comes to the society and the environment. And then for the harder coatings and antifouling coatings, the best scenario is applying the frequent cleaning with a low intensity, so that we don't want to make more like paint particles and biocide emission, and then while maintaining a regular dry docking recovery. And for the foul release coating, since we didn't apply any in-water hull cleaning scenario, so more regular dry docking or more regular maintenance is required in the best scenario. And then this is the kind of summary of the cost-benefit analysis. Again, it is very complicated, I think, but I will just summarize the kind of conclusion. So if you look at the operator saving part, you will see that the primary driver of the operator's cost saving comes from the reduced fuel consumption. As you can see here, like green colored values, they are almost 100 of the operator's cost for each scenario, which outweighs the hull maintenance cost. So based on this result, I can tell like proper hull maintenance can save a lot of fuel consumption in terms of the operator's saving. And if you look at the social and environmental saving, among the analyzed coating types, the foul release coating has the largest saving. And I think that is quite obvious based on our tool and based on our assumption in our tool. And that is because the foul release coating can have effective antifouling performance, so that it can reduce the emissions caused by the energy penalty. and which will reduce the human health impact and climate change impact, and at the same time minimize the release of the biocide so that it can reduce the marine ecotoxicity damage. And if you look at the RoPax 1 and RoPax 2, where the ship is operating in the Skagerrak and Kattegat, you see that the largest saving for the socio-environmental saving are coming from human health and climate change, which are mostly caused by the energy penalty. On the other hand, if you look at the RoPax 3 and RoPax 4, where the vessel is operating in multi-flow river, we can see that not only human health and climate change, but also marine eutrophication caused by the nitrogen deposition can be significantly reduced in this area. But as I mentioned, they are all the best scenario. So you have to have best scenario so that you can reduce a lot of savings when it comes to the social and environmental damage.
Wait.
Yes. Please.
If we focus on RoPax 1,
Yes.
all release seems to be a better option.
Yes.
But what does it make? What is it that makes it a better option? It's really the marine ecotoxicity index.
Oh yeah.
It has a big weight, doesn't it?
This is based on this is the best scenario, but compared to the baseline scenario, which means baseline was
Agreed, but if you rank them between them, if you have to choose between these three fouling, you will go for foul release because it gives you more operator savings and better socio-environmental savings. Looking at the table, it looks like, at least for the socio-environmental savings, the big advantage. Every copper is better on every point except for marine ecotoxicity, and that changes the ranking quite a lot.
Yeah, maybe I didn't explain in detail, but this 74% is the based on this value. So which means if you multiply 4.8 and 10.4%, which will be less than this one. It was complicated, I accept. But anyway, yeah, this value is not absolute compared to the other coding type. So maybe you have to think about the total saving, and then to get the better understanding, I think you have to multiply this and this, but at least you can see that it will give more savings when it comes to human health and climate change, right?
Copper will give more savings.
Yeah. No.
Okay.
Sorry. Yeah. Sorry for the.
Okay. Now okay.
Sorry for this image, but.
Okay. Now I see.
So you have to calculate. Yeah. But what I wanted to highlight is what is the main saving in each scenario. So that is why I used this. So if you sum this percentage, then that will be 100.
Okay, no. That's why. Well, okay.
Yeah.
That's a distribution of the savings. Second question: the fuel saving nowadays are linked to socio-environmental savings because there's the tax system like Fuel EU that comes into play. Are these mechanisms included in the tool?
Sorry, could you repeat?
Taxes on emission that are in place, like Fuel EU taxes. Are these modeled?
No, I don't think.
No, it's not included. No,
it's not.
It will make changes.
Yeah.
When it's added.
Sorry?
It will give changes when it's added.
Yeah.
When you add it, it will be, the fuel will be
more dominant, right? Yeah. I think that's a good suggestion. I think there will be more updates regarding EU taxes, and probably we can think about like CII or EVIs, etc., related to the index in the end. But I think that is a good suggestion. But so far we haven't included, so which means it will make it more significant in the end if we include taxes.
Maybe we can also mention that for the final release coating, we're assuming, or our assumption is that it has no marine ecotoxicity. So, but as you mentioned, there are a bunch of other substances that we are not really, we don't know so much about. So that will be included in the updated version.
Yeah.
But now also the marine ecotoxicity from final release coating is 0.
Yeah, right. I move to the last slide. This is the last. So I want to summarize my presentation today and our case studies. So HullMASTER is a decision support tool that can comprehensively calculate a life cycle costs related to the biofouling and the hull maintenance activities. And then it can provide a specific recommendation for the sustainable hull maintenance practices. And then we are working on the expanding into the European sea scale, as I mentioned several times. And then based on our finding through the case study in Baltic Sea, we can say like potential, if we are applying the optimum or best scenario, we can potentially save like this amount of money. But of course, it cannot be absolute, because sometimes maybe the business as usual scenario will not be the same as we have set. So the actual saving could be lower than this. And then also fouling intensity, depending on the fouling intensity, we have to think about the different hull maintenance scenario. That is obvious. And then among the analyzed coating type, we found that like biocide-free foul release coatings seem to be a promising potential option. But as we have already discussed, there are something more to be included. And even regarding the mechanical damage, maybe it is not the best when it comes to the practical consideration. So, so far we haven't included this weakness point, but in the end, we will somehow cover this part as well. And I would like to highlight that our case study are not universally representative of all vessel types and all the regions, right? So if you want to know your right solution of your vessel, then you need a ship-specific approach using HullMASTER. So you need some specific information like ship design characteristics, operation profile, operational region, and the environmental conditions of your vessel's sailing. And then also you need to consider what is the possible hull maintenance strategies that you can use. And then run the simulation, then you get the right solution. So yeah, that is one thing that I want to highlight. And as I already highlighted several times, there may be some impacts from the items that we haven't included in our tool. So there can be some uncertainties. However, I think I believe that this kind of our tool development and our research continue to improve in a way to contribute to our society and contribute to our environment. That is what I want to say for the last comment. Yeah, so that's it for my presentation. Thank you so much for your kind attention.
We can maybe we have questions more. Yeah, you can just go ahead with the questions we have received, because I think this question, I will read it out here. It's regarding who has committed to using HullMASTER, who sets the requirements that the shipping companies in the Baltic Sea should use this tool. And I will say that it's of course based on so far our partners in the research projects for how we have collected the first data to be able to illustrate all this. But then it's open and freely available, and we can, of course, assist in that. So it's not about that anyone has like done a commitment in that sense from someone else than from their interest in getting this data. And the requirements, who sets the requirements that the shipping companies use the tool? Yeah, so that is not a requirement for anyone. It's based on interest. And we are, of course, aware of that there are other tools developed around in the different initiatives that look partly at the same thing or look at the same thing. But again, this is then research based and free, and that's what we believe is the way. And
There are more questions.
more questions. If electricity penalty in the comparison of different maintenance scenarios, slide 97. Do you recall slide 97, Ron?
Go back to it if you want.
Because we didn't include.
No.
Yeah, I mean, we didn't include using the electricity, but we can set the percentage of usage of the electricity so that we can consider that. But according to our case studies, we haven't included.
I'm sure if you already responded maybe to this hull cleaning on. We are aware of ships with hull release coatings that are cleaned regularly. So underwater hull cleaning is not 0%. Is the question or the argument? The postpone, yes, true, but we don't really know yet. Or we need more data to be able to say. Or Erik,
I think our assumption was partly based from discussion with paint manufacturers, so included Hempel, that they do not recommend ship owners to clean on a hull that is coating with hull release coating. So it's
but maybe that
and we use that assumption, but then it's strict to know how frequently it is used and also about what damage that will have on the coating, etc.
I have recent contact with, of course, with the paint companies and shipping companies. I mean, if I have a discussion with the paint company, then they, of course, recommend not to clean on the hull release coating, because there can be damage in somehow. Of course, I mean, in water cleaning company, they argue that their fouling intensity can be adjusted so that it will not give any damage on the hull release coating, but still nobody knows. And then, but if I have a discussion with the shipping company, they are just trying to apply the in-water cleaning for any kind of coatings, because once they have seen the fouling on their hull, then they want to clean it. So that's how they think. Maybe sometimes they are not considering the characteristics of the hull release coating made of the silicone, or they just want to do that in that way. But as Erik and Lena mentioned, we are developing this tool from the academia perspective. So in that sense, we need somehow more clear understanding and explanation based on the paint manufacturer. So that is why we didn't apply in-water hull cleaning for the hull release coating for our case studies. But if you want, or if the shipping company want to include in-water hull cleaning case, then still you can apply in-water cleaning using this tool. But in that case, we cannot guarantee how the damage will be affected into the result, because, as I mentioned, we haven't included any mechanical damage possibility. So if there's something happen, then which will not, the coating will not work against the biofouling attachment, right? So that is the really important part, and I think we cannot model that due to the damage, and how will the biofouling grow on the damaged part. It's very tricky part.
As you say, and I think it's where we are now, that this is the data that we will really like to include what different, based on how cleaning data and different things. Something more around that. Yes, that of course, at least historically, pulp release coatings difficult to be due to mechanical damage, but also things are happening here, the paint development. So yeah, we need to include the latest as well. Sure. Hard foul release systems. Question from Lois.
Yeah, sorry, that was me. Yeah, because we're seeing innovations in the coatings market now. From my perspective, what we've done at Lloyd's is to try and give a scenario to our customers, so that we've asked our paint customers to provide data to say how their coatings react to cleaning and if they remain efficacious after cleaning. Some say you don't need to clean. Obviously, I respect what Hempel are saying there as well for the elastomeric coatings. But I was wondering if you were looking to include all of the innovations in the coatings environment now, including the harder foul release systems. I'd be really interested to see what the data was like with those systems as well.
Well, at the moment, we're not doing that, because since the efficacy data that Yang Rong showed, that is that originates from a 1-year field study that take a lot of resources. But on upcoming projects, that will for sure be interesting to include innovative programs.
Thank you.
Yeah, thank you.
Cost benefit analysis, slide 107. Maybe that we had in audience. Yes. So I think we have been through the ones from remote. Yes, please, Anne.
Yeah, so I guess this tool can be updated continuously. I mean, because there are coming new paints, there's new things going on. So, do we have any like long-term financing for that, or is it have to?
Looking at WhatsApp.
I think we need to bring it to Chalmers to see an argument around this to ensure that, because it's a really good point. And,
I think it's such a good tool, and it's so
Development, maybe. New projects. That's how Poly 2 came up.
Yes.
But not for maintaining.
No. But it's a good point that we need to ensure.
tool.
Yeah. Somebody in this room, I think it's a very good idea and want to.
Yeah, that's true.
Yes. So maybe some. Or do we have more questions? Otherwise, some final. We're back to this slide, which I think captures it in a good way. That to make this tool as useful and complete as possible, we really appreciate your input in the process. And if you come up with questions or ideas afterwards, you are welcome to reach out to any of us. Then I forgot to ask also beforehand, but the presentations, is it so that they will be available from Lighthouse?
We have this, we're quite strict with presentations, so we never send them out if they aren't asked for.
You need in that case to ask for them.
So if you send an email to us and say that you want them,
and we need to check, of course, with all
but you need to
So you can give us a version that actually can be sent out.
Yes.
Yeah. Was there more things? Yes, you have mentioned already that you can find more about our work. Point you said on the antifouling, HullMASTER antifouling. I think you will reach the group, and there is also a way to find the HullMASTER via the QR code. I will just mention briefly that the companies that have been partners in the project, they will be invited to individual meetings further on when we have analyzed everything. We have still some months left. The final report will be for Hall 2 will be delivered in the spring. Looking at you because I don't have the dates, but it's coming soon. So there will also be a way to read around this besides the papers that we have referred to.
And the first report
The
is
first report,
available on our website.
yes, true. Yeah,
So if you're interested.
yeah, that is good. So yes, from here.
Yeah, thanks everybody for participating both in the room here in Gothenburg and you online. It's been a pleasure.
Thank you.
Thank you.
For those of you who like to come to Lindholmen for seminars, you're very welcome next Tuesday. Listen to Nicholas and some other people as well, talking about wind propulsion in theory and practice.
And for those who would like to join together for lunch, we are planning to go down to the entrance. That is just down in the first floor or the entrance floor. Yeah, so please just. Thank you.
Thank you.
No, thank you.
Okay.